So we talked about the mean value theorem. Welcome to Calculus at the PM 5.2. Mean value theorem continued. And we talked about it on Friday a little bit, about 10 minutes or so. And it seems pretty simple, and it is more or less. The idea, the concept is mean or average value in common words. Average is not a precise word. Between 2 points, you just take their average rate of change. That's really taking the slope between the 2 points. If the function is continuous, 1, 2, if the function is also differentiable on that same interval, there's at least 1 point where the slope of the tangent line is the exact same as that mean change, mean rate of change between those two values. It seems pretty simple. Just to see if we have this in here. Well, before I get to example 2 there, I'm going to just see about something here and just take a look here. So mean value. So if I have a function A to B, I don't care what the numbers are. I'm going to change things every once in a while. Stuff like this. So if I have this function, I'm going to group it. It is grouped, okay. I'm going to just get my infinite cloner here. So first, if I had this function, would the mean value theorem apply to this function? Is there a spot on this graph where the same slope occurs? Yep. You're saying yes. How many times actually in this particular case? 3? 4. There'd be 1 there. Okay. There'd be 1 there. I heard 4. Yeah. There'd be 1 there. So the mean value theorem, what are the 2 conditions that are satisfied before you even consider it? It's continuous and it's differentiable. Okay? Then I said same values, right? Now, will the mean value theorem work in this particular case? It doesn't work in this case, like you can't guarantee it without knowing the function, right? It actually does have a spot though where the spot, it has 2 spots, looks like right about there, but you can't, and also then right here, but you can actually apply the mean value theorem to this function because in that interval, this point is not differentiable, right? Does that make some sense? Even though there are 2 spots. It doesn't mean that they don't exist, it's just that the mean value theorem doesn't apply to this and it doesn't guarantee that 2 spots exist. Do you guys follow that? So just because you can't apply the mean value theorem doesn't mean that you can't find spots where you might have the same value for the derivative as you do for the average rate of change. Does that make some sense? So the mean value only guarantees, and then you know for sure to keep looking. Okay? And then if we had piecewise functions that are linear, we could come up with all kinds of examples. Okay, so back to where we left off here. Example 2. There. Well, what were we supposed to do again? Oh, right. State whether or not the function satisfies the hypotheses of the mean value theorem, continuous and differentiable. And if it does, find that value of c that gives you that equation. So, question 2 here, we've got 1 over x minus 1, a rational function. And it's on the interval 0 to 3. A, does the mean value theorem apply in this case? Take take a look first. It doesn't. Why not? For x is 1, we have a vertical asymptote at x equals 1. Gotcha. So, vertical asymptote at x equals 1. Therefore, it's not continuous on this interval, right? Inclusive, the mean value theorem doesn't apply. Okay. Now, if I'll just wait. Sometimes it's important to actually be real careful with how you say your sentences. Now, I don't always have the best sentence or whatever here, but I'm trying to model, have complete answers anyways. Especially when there really isn't any calculations there, there's something I might be looking for. It's not just a yes, no always. You know? A reason and a conclusion on those ones. I think previously, did we just say, yeah, it's a polynomial, all polynomials are continuous and differentiable. They're smooth curves. Here, we know there's a monkey wrench. If I changed one thing to either this or this, the mean value theorem could be applied. If I change one thing in the interval, what could I do to have the mean value applied? I could change either one of these numbers. What would I do? Change it to 1? Not 1. 1.1, 2, 3 halves, something greater than 1, then it misses this, right? Or if I changed one symbol or number in this expression, and I still had 0 to 3 as my interval, how could I change that to have the mean value theorem apply?
X plus 1.
X plus 1, because then negative 1 would be the asymptote, the vertical asymptote. It would not fall in that domain that was given there on the interval 0 to 3. There's an example, right? You could also have x minus 5, like could be on the right-hand side of the domain. I knew you guys were coming. Okay, so there's ways, just so you can interpret things. And who knows, there may even be an actual, like if you took the slope from 0 to 3, there may be two values that actually do satisfy, or not satisfy, they don't satisfy the mean value thing, but there may be a couple of values that actually do have the same slope as the average rate, but they're not guaranteed by the mean value thing. That's all. Actually, I suspect there probably would be. Actually, I'm not sure. I'm not going to look into it either. Now, another thing in this section is increasing and decreasing functions, so on. Now, before we get to this, though, and this is just a watch and see here, I want to just talk about, and just do some messy drawings here, intuitively, what's an increasing and therefore increasing and decreasing function. Now, I want you to just watch, pay attention. I guess I'll do that. I'm only using the first quadrant. just because we're familiar with that. Group, then I'll clone. Okay. I'll just continue grabbing things if I need to. Increasing and decreasing functions. Intuitively, I hope you understand what an increasing or decreasing function would look like. If from left to right, always go left to right from the picture. Would you say from A to B, oh, I didn't want, I drew it too soon here. I'll just do it this way. Is this an increasing or decreasing function? Increasing. From left to right, the values continue to get larger, the y values, the f of x function values, right? Okay, so intuitively you guys have this understanding. What about, now I'm going to more or less keep the same endpoints. I might have to adjust it a bit. Now, I'm trying my best. Is this an increasing function? Yeah. Does it ever decrease is really. There's even a point where you might say, well, here it's not increasing or decreasing, it's actually a little higher there. But right there, it looks like a slope of 0, and it is. I was trying to draw something that looked like a slope of 0, but it never decreases. So as long as it, yeah, lessons. As long as it doesn't start decreasing, and it's only 0 for a finite, accountable number of times, you could have had between here and here. Okay, well, I'm drawing it too snaky there. But you could have several points, a couple of points where it hits 0 as a tangent, slope of the tangent, but it's still increasing. And then I think decreasing, not too, if I start here, to end up here, that's a decreasing function. I started sort of 0 at the start or whatever here, right? But the minute I have, I'll just put this here. Increasing or decreasing between, I'll call this C and D. Overall, the average is decreasing. But it's a bit of each, isn't it? There's from sort of here to here, it looks like it's decreasing. Here, in between here and here, it's increasing and then decreasing for the remainder to C. So you don't go with the overall, though on average it is decreasing, but there's 3 distinct sections, right? What do you know about when it changes from decreasing, so it's decreasing here, generally going down, to increasing? What is the slope of the tangent line when it switches from increasing to decreasing? 0. Those, we have the basic ideas. They're actually simple concepts. Now, we'll get into the calculus and see what this means, okay? So, we have this written down. This is your notes here. Increasing, decreasing, interval test. We kind of know what we're looking for. Suppose f of x is a continuous function on the open interval C to D. That's not including the endpoints. If the derivative is greater than 0 for all values of x in between C and D, with the exception of a finite number of points where you might have a derivative giving a 0, or it doesn't exist sometimes. More about that later. Then the function is increasing on C and D. Now, what does the derivative, this here, what does this mean? Okay, in greater than 0, it does mean it's going up. The slope of the tangent line is going up. Think words, one word. Instead of saying greater than 0, I could say what kind of number? Positives. Okay. 2. Because some people get screwed up. What do they mean, greater than 0? Okay, positive. So if I look back at what we gave as an example of an increasing function, the derivative is positive, right? It's climbing from left to right. The derivative of the tangent line here is positive. It is zero-ish, right about there, but it's only a finite, a countable number of times. When I say finite, that would be as opposed to, say I had this piecewise function. Flat, and then you could not call that red function increasing. Why? You're saying it does go up from left to right, and it does, but it's this finite number of points where the derivative equals zero. There's a whole batch of points there where you had the derivative equaling zero, right? On the red thing that I drew. Okay. But the do not exist. Just trying to think of one off the, oh yeah. Here's one. Cube root of x. You ever, if I have something like this now, this is a shape sort of like the cube root of x. And it doesn't have to be a piecewise function, that's why. What if I had this point from here to here, and it went, I'm going to have to redraw this over. Okay. Between what I just drew in blue, C and D here, where does the derivative not exist? Well, it's going straight up, right? Infinite. You see now it's still a continuous function in this case, right? Okay. This is still considered an increasing function because there's only one point where the derivative doesn't exist, right where it's just going sky high. Okay? Now, I'm not going to go through all the negative things or the decreasing stuff, but it's the same idea. If the derivative is less than zero, so if it comes out to be a negative value on that interval, C to D, with the exception of a number of points where you might get a zero or it doesn't exist, then it's decreasing on C and D. It's simple to understand if you have a diagram, and that's the first thing. So we call it the first derivative test when we're looking for this. If C is a critical number, and a critical number, what is a critical number? Two possible candidates, where the slope of the tangent line is zero, he's horizontal, right? Or it's not defined because it's straight up and down. We saw a picture or something like that. Then, the function has a relative maximum at that value C if the derivative switches signs from negative to positive. And we will use this phrase, f prime of x switches signs from negative to positive, and then vice versa. The function has a relative maximum at that value C if the derivative switches signs from positive to negative. Now, if you think about this, it isn't that bad. I'll just draw one where we definitely have a maximum. How about this? And I'd invite you to maybe sketch this here too. If I just have, we'll just draw a quadratic like this. A portion of a quadratic in between A and B. And I think it's pretty easy to tell. Just jot this down in the corner. This would be a maximum that occurs here, right? At the vertex of the quadratic. I'm not giving the equation on purpose because we're not focused on that right now. This would be C, right? F of C would be a maximum. Oh, Nat. At F of C. Or the maximum value equals is better than at. My mistake, I'm just doing this on the fly. So what occurs at x equals c. But let's see how this first derivative test would work if you didn't have the graph and you had the function x squared, or negative x squared, I guess in this case. Negative x minus 5 or something like that, all squared, plus 8. something like that. Now, according to this, if it has a max, that's what we're saying, it has a max, at that value C. Does the derivative switch signs from positive to negative? Well, it definitely occurs at a critical number. This is where the slope would be 0, right? What would you say if you sketched in the slope of the tangent line? What's the slope of that between A and C? To the left. Positive, right? And then, so it switches signs from positive, it's 0, and now it goes to negative. Does that make some sense then? So you really, if you truly understand this, you don't have to memorize the first derivative test. If you just have some simple shapes in your head, a maximum looks like this, oh yeah, positive slope, negative slope of the tangent line switches signs. That's how I know it's a maximum, and vice versa for the min. Now, let's try these out together here. You might not even have to do calculus for A. Actually, I hope you don't, but let's do calculus anyways. What do we call f of x equals -7? What kind of function is that? It's a constant, so it's going to be a flat horizontal line. Sorry, I won't be able to help you right now. Or is it just handing in it? Oh. Thank you, dear. Now, let's put this away to correct. So yeah, and the derivative of a constant's always any constant. 0. Derivative of cos of pi thirds. E to the 7. E to the x. E to the x, caught you. That wasn't. Didn't catch you, I mean, caught somebody else. Okay. So, is it increasing or decreasing? Neither, right? No extremism. Actually, you could argue, or could you? Nope, you couldn't argue. Okay, how about the next one? Is this the best form to do calculus, to do a derivative on it? I'd say I'd play around with this and distribute the divide by 2. So before I do calculus, I'm going to go 1/2 x minus 6 divided by 2, so 3. Same equation, right? Just makes my life easier. You're by all means, go ahead and do it on that original function too, if you wish. But the bottom's a constant, so I wouldn't. So, when we do that, we get a derivative. And it's a rather simple derivative, it's half, right? So, when is this function increasing or decreasing? And is there any maxes or mins? So increasing, decreasing. If the derivative is greater than 0 for all of the x on a given interval, then it is increasing. If it's negative, it's decreasing. In this case, we got positive 1/2. Does it ever change? No. No. So what would we say it's increasing on? Let's give interval notation.
Negative.
All numbers, yeah. It's always increasing. Now, I hope sometimes when you start doing calculus without a calculator, we're easing our way out of that with a lot of things. I'm hoping that you look at this and you say, what kind of function is this? I didn't ask first because you probably have the answer then right away. But mx plus, it's a linear equation. And it is. I'll just have it in disappearing ink here. -3 says down here, and then it's increasing with a slope of 1/2. Rise of 1/2. Rise of 1 forever. So it makes sense. It's always increasing. There's no max or min. It goes high, sky high forever, right? Okay. Now, as I mentioned before, We knew this was a constant, this is linear. We now know this is a quadratic. So you should just think, what kind of answer should I get? It's a quadratic. So, how does this one open? When I say open up, yeah. How can you tell? You're right.
Because it's a positive.
Positive a term. Yeah, x squared, the lead term, if it's in that order, is positive. And with quadratics, you guys think like that? Happy face, positive lead term.
Yeah, that's what we think.
You should. Will this have a max or a min? Minimum. So we know what kind of answer we're going to get. We should get one min. This should it should have a decreasing portion first, up to the vertex, and then an increasing portion. Remember how you guys used to do find the vertex by completing the square? It's not that bad actually, but it's way quicker to use calculus. Because I know the vertex will be where the derivative of the tangent line is 0. Something like this. If you ever help someone in grade 11 with their math, you say, oh, the vertex, I could tell where it is. You could do it a lot quicker. So, the first thing we'll do is the derivative. So we know what kind of answers we're looking for. The derivative here is 2x minus 8. Now the possible candidate, singular in this case, because we kind of know what we're looking for here, is where it's either 0 or undefined, but we're only going to get a 0 with a quadratic equation. We know that. So we set this 0, find the critical number. By all means, if you saw 2x minus 8, you could factor it, blah, blah, blah. Like skip into that. And our solution, 2 times something gives me 0, well, x minus 4 has to be 0 there. And to solve x minus 4 equals 0, you got 4, right? That's the critical number. Now, you could think about this one, probably, and figure it out. Because we know it's opening up. Right? But I want to get a habit going on here and sign analysis while it's simple. Now you don't have to label this every time, but this is what I mean by sign analysis. I'm going to get you to write out the factors and just draw a very simple number line. I will include even positive 2 and then x minus 4. We know where x minus 4 gives us a 0. I only put down what gives me zeros. I don't necessarily put the number 0 on my axis here. Okay? Now the reason why I do this is when you got something that's a cubic equation or something with radicals and several parts to it, you want to be able to organize your thoughts easily. Now, is 2 ever negative? No, it's a constant, so it's always positive. So I'm going to put that in here, both to the left and to the right of 4. But 4 is interesting because it's 0 here, that's where the derivative is 0. And to the left, if I put in 3 or anything smaller than that, I get a negative value, right? Test values. Use the easiest test values you can think of. So negatives, positives. And then I think with these 2 factors, the 2 and the x minus 4, on this side of 4, I have a positive number and a negative number combining, right? It's going to always give me a negative. Okay? 4, it's neither fish nor fowl, it's 0. Right? That's the vertex. And this will always be positive here. Now, like I said, this one here you could tell, I think, how it was working just by knowing a little bit about x squared minus 8x minus 20. But I want to give you tools so that when it's tougher, you can do it. So, we can now answer our question. Because remember, we did the sign analysis of, this was the derivative, right? That's what we're talking about here. not the original function. It describes something about the original function. So, increasing, decreasing. When is this function increasing, decreasing? Which first? Give me, what's that? Increasing. When is it increasing?
After any real number greater.
Okay, good. So, we'll say it's increasing on, I don't know if I left, well, I write bigger. Hopefully you can have this. Increasing on, we'll give the interval, bless you, 4 to infinity. Since, what was that reason? Increasing. Oh, goodness. I know this, but f of x is a continuous function, blah, blah, blah. If the derivative is greater than 0, with a few exceptions, it's increasing. So we're saying this backward. It's increasing on since f prime of x is greater than 0, and I'm running into things, so I'm going to do this here. I'm going to see if I can move that there. Okay, there. I won't have to have my slope anymore on my writing. So, since f prime of x is greater than 0 on the interval. Okay? Does that make some sense? You're going to actually memorize to always, like, it's going to be automatic. If you say something's increasing, you're going to say since and give the reason greater than or less than. If you say something's decreasing, actually, and I'm not being too careful either, the function f of x, and I should have put that here, f of x is, so f of x is, and I'll be out of the way, I know you can't see me, is decreasing on, well, the negative values, negative infinity to 4, since the derivative is less than 0 on the interval. Okay. By the way, those things, just so you know where things fit in, this is regular calculus over here right now. The mean value theorem itself is not, but increasing, decreasing, those are actual cut and paste from what I have for notes for regular calculus. Just so you know, most of this is regular. And the last thing, it said identifying extreme maxes or mins, if possible. And find the coordinates. Okay, so we only have the x coordinate. What's the y coordinate? How would we get it? So we put 4 into here. F of 4, 16 minus 32 minus 20. So minus 52, right, is the negatives. 16, oh goodness gracious. So you get a negative answer. Okay, negative 36. Yep. So, the coordinate of, no, let's do it this way. Sorry, I'm getting distracted with that. 4 comma negative 32 is a minimum. It's actually an absolute minimum. I just didn't write it down. Since now, what's the since statement? What proves that it's a minimum? Switches signs, that phrase. Since what? Look it up. Look it up. minimum switches signs from the derivative, switches signs from negative to positive. And we're going to have to include that in all of our answers.
And isn't it negative 36?
Is it negative 36? My arithmetic is bad? Okay, let me see here. What was it? 16.
Because 16 minus 32 is a negative 16.
Oh, 32 is what I was subtracting. Okay, and you said 36 too, didn't you? Sorry. I was still rumbling numbers in my head. Thank you for correcting me. Where was I? Minimum, since f prime of x switches signs from negative to positive at x equals.
Would we write as an absolute minimum?
You can do that too. Yes, you could. On some of these questions, though, I'm not going to require you to know whether it's an absolute or local, just because sometimes the functions are so crazy. So, but in this particular case, it is an absolute. Yes. But this one, there's no doubt about it. Okay. So those are basically recipes for your answer, basically. Either you say the derivative is greater than 0, derivative is less than 0 for increasing, decreasing, or switches signs depending if it's a max or a min, right? Now, the last one, x cubed. You know the graph of it? Yeah. So we should confirm what we know. I see some people kind of knowing it. Right? Now, I actually had a picture of this up earlier without the equation, but something like that. You can tell this is increasing. It hits 0 once, but it doesn't change to negative, does it? But let's just go through this because you'll have trickier functions sometimes. So, looking for the critical number, you do the derivative. If you didn't know this already. 3x squared. Okay, when is it 0? Only when x equals 0, that's a critical number. Right? But if I do a little quick sign analysis here, I say, well, 3 and x squared. 0 is my critical number. That's all you put on those. Well, 3 is always positive. Sure, x squared hits 0 once, but it's squared, so all the negatives become positives too, right? So that is an increasing function for all values. No max or min, right? No extrema. So, f of x is increasing on all values. My comma doesn't look like a comma. Now, the way I state this, look back here. I was just going to go back up to here. Is this a contradiction? Increasing? Okay. With the exception of a finite number of points. So, but it's with the exception of 1 point. It never switches to negative, though, does it? So, We could state that, okay? Is greater than 0. In this case, I'm going to say with the exception of 1 on the, let's leave this in there, integral. How do you do sign analysis? Well, I'm doing it on the derivative into its factors. And I'm saying the constant as one thing. The constant's always positive. Just sometimes people get used to just writing down the factors, like x squared or whatever. And then they had a -2 in front of there, and it reverses everything. So I want you guys to get in the habit, if you have a constant, of just writing it out too, okay? So it's really 3 times the x squared, and if you had more brackets, you'd work with those. Now, I'm wondering here, because I know the time is short. Yeah, I will do one more. And it's a doozy. We start, and this is where the sign analysis actually makes some sense, okay? Now, you'll notice, I left a lot of space for this one. It's not going to be as short. First thing you do, look for critical numbers, right? So you do the derivative. I hope you can see -4, okay? Terrible at talking and writing.
You don't need that skill for being a teacher.
Good thing I don't have it. Pressure. Okay. I'm going to find the critical number, right? That's when the derivative is 0. I'm going to factor out a -4. I'm thinking there's more to that factor I can factor out. -4 and x. And that switches the sign. This is perfect, eh? Then you can keep going, right? Now the sign analysis will have a few more things to go with. So, we've got 3 critical numbers here, but I'll wait for a second. Okay. What are our critical numbers? This critical number, 0. This critical number, to get a 0 out of that bracket, 3. This critical number, -3. This time the sign analysis will have a few things going. Now, are we all good up to here finding the critical numbers? I'm hoping. This time, like I said, the sign analysis of the derivative. Well, I'll go with this. I'm going to list my factors here. Whether you want to write it, I'm going to write it separately this time. -4, the x, x minus 3, x plus 3. I'm listing my derivatives factors here, right? That's what I'm doing here. Then I'm going to draw a number line for the x's. And as I go through this, let's see here. Well, you know what I'm going to do, just to make things a little, don't worry, you don't have to erase anything, but just to organize this a little different. -4 due to the x. 3, x plus 3. Just so you can see, because my lines are crooked probably. Is negative 4 ever? No. We'll come back to that. So, my critical numbers are 0, 3, and negative 3. So I'm going to put my negative 3 here, my 0 here, my 3. Okay, I'm including 0 because it's a critical number. Now, as I said before, negative 4 is always negative. I'm only listing it here so you don't forget about it. If you wished, and consider this as one factor, that's fine as long as you take that into account, minus 4x. You don't necessarily have to have that separated, but don't forget about it. So, when it's smaller than negative 3, it's negative. In between 0 and negative 3, it's negative, and so on. Always negative. My x, I like to list my 0 first, so x is 0 at 0. Anything smaller in that factor will be negative. Anything larger is positive. So I'm just imagining if I plugged in numbers. So I plugged in the number 2 here. Oh yeah, it's positive. Okay. That's good. So that's what we're doing here. Did you guys ever do this for inequalities? When you guys solved quadratic inequalities? You did? Long time ago. Grade 11? Well, it would have been grade 11. But, I mean 20? Okay. Oh, that was grade 10 then. If it was Ms. Constant.
It would have been grade 10, but it's 20.
Right. Foundation's 20. Okay. Got it. So, we get a 0 here when we plug in 3. Anything larger than 3 in this factor, give me a positive. Anything smaller is a negative. Okay. If you have, you can see the trend here. I get a 0 at negative 3 in this factor. Anything smaller, negative. Positive. Positive. Now, don't get stuck in this rut of just finding your 0 and putting negatives to the left, positives to the right. Sometimes you get a factor, and I'll just put it down here. What if it was 3 minus x instead of, well, okay, I should have done that in green. But anyways, if this factor was 3 minus x, you'd still have the 0 at 3. But do you see how it would have been backwards of the signs? Okay. So just take a second to think about what you're doing there. And usually, you have the x first. You can do it that way. Now, overall, this function's derivative. 4 negatives, positive. Odd number of negatives, 2 negatives, and 1 negative. Okay. What does that mean? If I asked you to do a rough line sketch with no curviness, the function would go, yeah, you see your hand going up, down, down. What he's saying is that, and this color, I'm not particularly caring what color it is, but do you guys see, up to negative 3, it's increasing. It's an increasing function. I'm just doing this just so you're aware, kind of like, this is what that means. It goes up. Now, there's some curviness to it. We're not worried about that, though, right? And then, from negative 3 to 0, it goes down. I'm not worried how low it goes. I'm just saying roughly, what does this mean? Then 0 to 3, it goes up. And then 3 and beyond goes down. Now, if you do something like that, I like to do that underneath the graph. That just means right away, without even thinking of definitions of maxes and mins, where are my maxes? Yeah, you can see it goes up, and then it goes down. And then 0 is a minimum. Yep. And it would definitely be a local minimum. One of those maximums is an absolute, one's a local. I'm not worried about which it is, though. Now, there's 6 minutes left, 7 minutes. We can answer everything now. It's just a matter of getting these sentences there. So it's increasing on. Let's say that. The function f of x increases on. Then, well, that's obviously negative infinity to negative 3. In union with, we can use that. You guys use that U symbol, kind of? In union with 0 to 3. Since yeah, f prime of x is greater than 0. In the intervals. And then, it's real nitpicky, eh? It's got to be precise. F of x decreases on the other ones. 3 and up. Since f prime of x is less than 0. Precise language. But you use it so much I don't call it memorizing. And then the mins and maxes. Well, with this one here, I'd give you a breakout. If you calculate them and stuff like this, you get 84 for the 3s, both negative 3 and positive 3. What is the 0? Oh, 0. It's 3. Yeah, that's easy. Okay. So what happens at 0? It's a minimum, right? Relative, local, occurs at 0, 3, since f prime of x which is switches. Signs at x equals 0. And the mins or maxes, not singular. I'm just trying to decide. It's not really absolute because there's 2 with the same height, so we're going to just say relative maximums. Occur at, I said negative 3, I'm going to double check, yeah, 84s. Negative 3, 84, and 3, 84. I didn't say how it switched signs. Nobody stopped me. The previous one. Since. I maybe said it, but I didn't say it. You can switch signs, but that could be a minimum or a maximum. I'm going back here. Signs from min, negative to positive. I'm squeezing it in. Sorry. And that's going to be all she wrote. Since the derivative switches signs from maximum, so positive, you're doing your announcements, eh?
Yeah.
Go. Okay. I'm going to stop the recording here, though. Just a second here. That's a